This is Lab 4 Oscillations. We'll begin with a brief introduction. The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We will track the observed position using Tracker and compare it to a computational model created via GlowScript. The models and fundamental physical principles used in this lab are as follows. Newton's second law, which relates the net interaction between the system and surroundings to the observed motion of the system. F net in this case is the sum of the spring force and the force of gravity, and F net can be calculated as a change in momentum over the change in time. The energy principle states that the change in the total energy of the system is equal to the sum of the work done on the system by the surroundings and the energy exchange between system and surroundings due to a difference in temperature. Delta E is equal to W plus Q, and the change in the total energy of the system is 0. For the preview of main results, it was found that the energy principle was demonstrated successfully as the change in the total energy of the system was 0. The experiment. The system was the mass, the spring, and the earth, and the surroundings were nothing. For the initial conditions, t equals 0 seconds, the mass was 0.402 kilograms, the relaxed length of the spring was 0.123 meters, the current length of the spring was 0.7 meters, the spring stiffness was 6.83 newtons per meter, and as the mass is released from rest, the initial velocity was 0 meters per second, and the initial position was negative 0.11051 meters in the x direction, and negative 0.62707 meters in the y direction. For the experiment, the first step was calibration. The length between the fixed attachment point and the mass at rest was set to be 0.7 meters. The origin was set at the attachment point and the y-axis was aligned with the spring. The x and y positions of the mass were tracked via Tracker using the point mass, and the data was plotted onto a position versus time graph. For the code, line 79 defines gravitational force near Earth's surface, line 82 initialized the spring constant, line 85 initialized the relaxed spring length, line 88 calculated the current length of the spring, line 89 calculated the unit length vector, line 90 calculated the stretch, line 93 calculated the kinetic energy, line 94 calculated gravitational potential energy, line 95 calculated spring potential energy, and line 96 calculated the total energy. Line 108 defines initial kinetic, line 109 defines initial gravitational potential, line 110 defines initial spring potential, line 111 defines initial total energy, line 114 calculates gravitational force, line 117 calculates spring force, line 120 calculates net force, line 124 applies the velocity update formula, line 126 applies the position update formula, line 129 updates the current length of the spring, line 130 updates the spring length unit vector, line 131 updates stretch, line 137 calculates the kinetic energy, line 138 calculates the change in kinetic energy, line 139 calculates the gravitational potential, line 140 calculates the change in gravitational potential, line 141 calculates spring potential, line 142 calculates the change in spring potential, line 143 calculates the total energy, and line 144 calculates the change in total energy. For the similarities and differences between data and model predictions, the change in energy was 0, meaning that the sum of the work done on the system by the surroundings and the energy exchange between the system and surroundings were the same. The change in kinetic energy decreased over time. The computational model and the experimental model were not exactly the same. For the possible sources of error, include not placing the tracker feature directly at the center of the mass for each time step, as well as improper calibration and errors in the code. For the first "what does it mean" question, I responded by saying the energy principle was satisfied for the model system as the total energy of the system was conserved, that is, delta E remained at 0. For the second "what does it mean" question, I responded by saying the period of oscillation from the x position data was approximately 1.6 seconds, and the period of oscillation from the y position data was approximately 1.5 seconds, and since the period of oscillation are different for both datasets, using both axes will produce more accurate results. In conclusion, in this lab, we were able to track the motion of a mass oscillating on a spring and determine if the energy principle was satisfied while comparing an observed model of the spring to a computational model.